12.2. More on the center of gravity. The outline of this video is as follows. We will begin by formally defining a crucial concept for equilibrium problems: the center of gravity. This is the effective point where the entire weight of an object can be considered to act for the purpose of calculating torque. Next, we will explore the important relationship between the center of gravity and the center of mass, and we will identify the specific conditions under which these 2 points coincide. To bring these ideas together, we will conclude by working through a practical example, applying our understanding of the center of gravity to solve a static equilibrium problem. When we analyze the forces on a rigid object, we must account for gravity. The key insight is that we can simplify this by using a special point called the center of gravity. An object is made of many particles, and gravity pulls on each one. Instead of dealing with all these individual forces, we can represent their combined effect as a single gravitational force acting at one specific location. This point is the center of gravity. It is effectively the average position of the object's weight. For example, the point where you can balance a long object like a baseball bat on your finger is its center of gravity. By placing a single upward force there, you can counteract the weight of the entire bat. This concept is extremely useful for calculating torques. We can treat the total gravitational force, which is the object's mass, m, times the gravitational acceleration, g, as if it acts entirely at the center of gravity. To find an object's center of gravity, we first need to recall a related concept: the center of mass. We can think of any extended object, like the one shown in the diagram, as being made up of many individual particles. Each of these particles has its own mass, which we can label m1, m2, and so on, and each is located at a specific set of coordinates. The center of mass is the average position of all the mass in the object. To find its x-coordinate, we calculate a weighted average. As the formula shows, we take each particle's mass and multiply it by that particle's x-coordinate. We add all of these products together. Then, we divide that sum by the total mass of the object, which is simply the sum of all the individual particle masses. A similar calculation would give us the y-coordinate. In short, the center of mass is the mass-weighted average position of the particles that constitute an object. We can also locate the center of gravity by analyzing the torques produced by gravity. Imagine an object is made of many individual particles. The weight of each particle, which is its mass, m, I times the local gravitational acceleration, gi, creates a torque about the origin. The total torque on the object is simply the sum of all these individual torques. The center of gravity is the special point where a single force, equal to the object's total weight, would produce this same total torque. This equivalent force is the total mass, m, times the gravitational acceleration at the center of gravity, gcg. Setting these two ways of calculating the total torque equal gives us the equation shown. The left side is the torque from the total weight acting at the center of gravity, xcg, while the right side is the sum of the individual torques. In short, the center of gravity is the effective point of application for the total gravitational force. This slide explains the crucial connection between the center of gravity and the center of mass. Our general equation for the center of gravity allows for the gravitational field, G, to vary in strength and direction across an object. But for most situations we encounter, we can make a very reasonable assumption that the gravitational field is uniform. This means the value of G is constant everywhere on the object. Under this condition, the G factors in our torque equation are all identical and can be cancelled out. When we do this, the equation for the x-coordinate of the center of gravity becomes the sum of each particle's mass times its x position, all divided by the total mass. You should recognize this as the exact definition of the x-coordinate of the center of mass. Therefore, the center of gravity and the center of mass are the same point as long as the gravitational field is uniform. For a symmetric object with uniform density, this point is also its geometric center. Let us apply our understanding of static equilibrium to solve this problem. The key is to recognize that for the meter stick to be balanced, the torques on either side of the pivot point must be equal. The pivot here is the string, located at the 25 centimeter mark. First, consider the torque created by the hanging object. Its mass is 0.50 kilograms, and its distance from the pivot, called the lever arm, is 25 centimeters. This object creates a torque in the counterclockwise direction. Next, consider the torque from the meter stick's own weight. Because the meter stick is uniform, its center of gravity is at its geometric center, the 50 centimeter mark. This weight creates a clockwise torque. The lever arm for this force is the distance from the center of gravity to the pivot, which is 50 centimeters minus 25 centimeters, giving us 25 centimeters. Since the system is in equilibrium, the clockwise torque must equal the counterclockwise torque, as both the lever arms and the acceleration of gravity, g, are the same for both torques. They cancel out of the equation. This means the mass of the meter stick must be equal to the hanging mass. Therefore, the mass of the meter stick is 0.50 kilograms. Let us walk through the solution to this quiz question. We can find the mass of the meter stick by applying the condition for rotational equilibrium, which states that the net torque on the object must be 0. The pivot point for our system is where the string is attached, at the 25 centimeter mark. There are two forces creating torques around this pivot. First, the 0.50 kilogram mass at the 0 centimeter mark creates a counterclockwise torque. Second, the meter stick's own weight creates an opposing, clockwise torque. Since the meter stick is uniform, we can model its weight as a single force acting at its center of gravity, which is the 50 centimeter mark. For the system to be balanced, the magnitudes of these two torques must be equal. The lever arm for the hanging mass is 25 centimeters. The lever arm for the meter stick's mass is the distance from the pivot to the center of gravity, which is 50 minus 25, also 25 centimeters. Since the lever arms are identical, the forces must also be identical for the torques to balance. This means the mass of the meter stick must be 0.50 kilograms. Let us summarize our discussion on the center of gravity. This is a crucial concept that defines the single, effective point where the entire gravitational force on an object can be considered to act. Its main purpose is to simplify our work. By using the center of gravity, we can calculate the total gravitational torque on a rigid body without needing to add up the torques from every individual particle. It is also important to understand its relationship with the center of mass. The center of gravity, or CG, coincides with the center of mass, or CM, under the very common assumption that the gravitational field is uniform across the entire object. For everyday objects, this is an excellent approximation. This leads to a simple rule for many common situations. For any object with a uniform density and asymmetric shape, such as a solid sphere or a rectangular beam, the center of gravity is located at its geometric center. The main takeaway is that the center of gravity is a tool that simplifies torque calculations. To wrap up, let us consider a couple of questions to check our understanding of the center of gravity. The first question asks you to think about the specific condition under which an object's center of gravity would be different from its center of mass. We have been treating these 2 points as the same, but this is only true under a specific assumption about the gravitational field. Consider what would happen if an object were so large that the gravitational field was not constant over its entire volume. The second question is a practical one. It asks how you could experimentally find the center of gravity of an L-shaped object using only a string and a weight, which is also called a plumb line. The key is to remember that when an object is freely suspended, its center of gravity will always hang directly below the point of suspension. How could you use that fact to pinpoint the exact location? Take a moment to think through these scenarios. They are excellent ways to solidify your understanding of these important concepts.